Hello guys, this is the first lesson that I'm going to post to help you prepare for the IMAT. This is on the subject of biology and we're going to start by some introductory biochemistry. So let's begin. First we're going to look at the atomic structure. I have chosen for the purposes of this lesson to just introduce you to the Bohr's model of the atom rather than more advanced, which will look into the chemistry part. Now, this is the Bohr's model of the atom. Bohr said that the atom consists of the nucleus, where there are protons and neutrons, and around it the electrons travel at circular orbits, which he called energy cells or energy levels. And he gave them numbers. He said that the first one is the n equal to 1. The second one is 2, then 3, and he gave them letters. This is the K, this is the L, this is the M. So we can see we have the sodium atom with 11. What is the atomic number 11? That means it has 11 electrons and 11 protons. So it has 11 electrons and protons. The K shell takes up to 2 electrons, it's filled. The L up to 8, and the M again up to 18. It only has 1 here. So what we deduce from the fact that the number of protons in an atom equals the number of electrons is that the number of positive charges in an atom equals the number of the negative charges in an atom. That means that the overall charge, the net charge, is 0. Neutral charge, that means 0. And this is called the elemental state. Okay. Now there are also neutrons in the nucleus, but neutrons have no charge. Now, I told you that the K takes up to 2 electrons, the L up to 8, the M up to 18. Why didn't I put 1 electron here, 2 electrons here, and all the rest to M? And I started filling with K, and then L, and then M. Because we fill the cells, the energy levels, from the lowest to the highest. So K is the lowest energy cell, L the lowest, and M the lowest that could get, the next lower. So if I were to give you the energy level of each of them, it will be K, higher L, and higher M, etc. But when an atom has all the electrons in the lowest available energy level, like the sodium right here, it's said to be in the ground state. But are there atoms that they don't have all the electrons in the lowest available energy level? Of course there are. Let's say that an atom absorbs energy. Energy is in the form of photon, which means light, or little quantums of light. So let's say light hits an atom. The atom must absorb energy. How it absorbs? The electrons of the atom absorb this energy. So if the energy bumps the photon, here is the photon, bumps into this electron, this will have more energy than this energy level, and therefore will be moved to a higher energy level. The atom then would be in an excited state. But will it stay here forever? Of course not. It will fall back down to its position by emitting the radiation the same level that it absorbed. Again, I'm just giving you an overall picture here. I'm not getting into details because this is the biology part of the IMAT and not the chemistry part. Okay? Why do we need to know the excited state and the ground state in biology though? Because when a chlorophyll molecule in a photosynthetic plant cell absorbs light energy, the molecule becomes excited and electrons get boosted to a higher energy level. And we'll see that the whole mechanism of photosynthesis is dependent upon this property. So, what are isotopes? Isotopes are atoms of one element that vary only in the number of neutrons in the nucleus. That is what? I told you that the atomic number, when we say that sodium has an atomic number of 11, we can deduce from that that it has 11 electrons and 11 protons. We don't know in the elemental state. We cannot say how many neutrons does it have. We need more information. The mass number, as it is called. So, and why we cannot? Because it is not stable. Different sodium atoms have different number of neutrons. Those different atoms of the same element, sodium, are called isotopes. Now, the properties of an element are the result of the number of electrons in the outer cell mainly, and generally how they're distributed, how the electrons are distributed within the multiple cells. Now, all isotopes have the same electron configuration. Why? Because they are part of the same element. And an element has a stable, in the elemental state, has a stable number of electrons and protons. But they don't have the same number of neutrons. But that would not affect their properties. Okay? Now, some isotopes are radioactive. For example, carbon-14. There is carbon-12 as well, but it's not radioactive. Phosphorus-32, sulfur-35. We use them in order to trace the pathway of substances. For instance, sulfur is being absorbed by proteins. Therefore, we can use the sulfur 35, which is radioactive, and therefore we can trace it. We can use it in order to view where the proteins are going. Now let's move in the bonding. First of all, I want you to understand what is a bond. A bond, what we call a bond, is a formation where two atoms stay together, close, together, next to each other by powers of electrostatic nature, but they stay together. This is a bond. When two atoms stay together and cannot be broken, cannot be separated without energy. For instance, this is a bond because those two stay together and cannot be separated without energy. Now, in order to understand how a bond is created, we need to understand why a bond is created. Because the substances that are being created when two atoms connect to create a bond have different properties than their atoms. That means that if I have the sodium chloride bond, it has different properties than sodium or chlorine. Different properties. Okay, so this is why we need bonds. Now, why they're being created, why nature creates bonds? Because you see here, this electron, only this nucleus pulls this electron, which means only this nucleus has force, electrostatic force, in this electron in order to keep it inside its cell. But when it's here, both nuclei pull this electron and it stays here. That means that the energy needed to keep the electrons in its position are lowered. That means what? That we're in a lower energy level when we are in a bond formation than apart. This is what I tell you here. Yes. The atoms in a bond are in a lower energy level, therefore in a more stable configuration. This is why energy is released when a bond is formed, and the reverse means that we must give energy to the system in order to break the bond. Now, what are ions? Let's see this sodium atom right here. It has 11 electrons. Let's say I take one of them. I will take that because this is the one I have access to. Okay, I will take this one because it's in the outer cell. This will be the first one released. And I will take this and I will remove it away. What will happen? Here I will have a sodium atom with 10 electrons and 11 protons. This is not called an atom, it is called an ion because it does not have a zero charge. It has lost some or gained some electrons. That means this equality is no longer true, and therefore we cannot call it an atom. This is why we call it an ion. So there are atoms that have gained or lost electrons. Anion is called when an atom has gained electrons. Therefore it has negative charge, because when you gain electrons, you get more electrons than protons. Therefore you get a negative charge. And so we have a negative ion. So that is called a negative ion. Okay. And this is a cation. We have positive charges. Here, 1 plus means it has lost 1 electron. Here it has lost 2 electrons. Now, the ionic bonds are the result from the transfer of electrons. Let's see this example. Sodium, the sodium atom, has 1 electron in the outer cell. The chlorine atom has 7. The sodium atom gives 1 electron to the chlorine atom, and therefore this has 1, 2, 3, 4, has a full outer cell with 8 electrons, and this has again a full outer cell with again 8 electrons. These together, these are closely stayed because the electron that it didn't give it totally, it acts again some pressure on it. This is called a substance, an ionic, and it is the sodium chloride. Now here we have covalent bonds. Covalent bonds are the result of sharing electrons. You see, a chlorine atom and a chlorine atom connect in order to create a molecule. Now we create molecules, and those 2 electrons are being shared by the 2 nuclei. They are being pulled by both nuclei, and therefore these 2 chlorine atoms stay together. Now let's try to explain electronegativity. Electronegativity is how much force each nucleus pulls, with how much force each nucleus pulls the electrons. Here, those 2 chlorine atoms, they have the same electronegativity because they're of the same element. So they act the same force at these electrons. the shared pair of electrons, is being shared equally. They both pull it with the same force. But let's say we had two elements that the one is more electronegative than the other. That means the one element acts more force, pulls more the shared pair than the other one. Then we have example water. You see, the oxygen pulls the pairs more than the hydrogen, and it goes more to its direction. It shifts away from the less electronegative towards the more electronegative. And now we've got some phenomenon charges, because since this pair has shifted towards this, a charge is created here, a negative one, and here a positive one. And this is called delta plus and delta minus. Now, the first example, we call it nonpolar covalent bond, which is when two atoms have the same electronegativity, and therefore they both attract equal the shared pair of electrons, and the bond is called nonpolar. But when the atoms in a molecule are different, for example, here, hydrochloride, or here, water, each atom does not have the same electronegativity, and therefore the shared pair of electrons is not equally attracted. This is because the shared pair of electrons is attracted more from the more electronegative element, and we have as a result the creation of polar covalent bond. These charges are really important. You need to understand it. So let me explain it to you one more time. The hydrogen has one electron. The oxygen in the outer cell has 1, 2, 3, 4, 5, 6. So it needs to create two pairs. So it shares that electron with that. This is a bond here, a covalent bond, and it shares that electron with another hydrogen atom. But because oxygen has is more electronegative than hydrogen, it pulls this pair towards here. Therefore, the hydrogen now has no electrons, and the oxygen has one more. Therefore, a delta minus, a negative charge. And the hydrogen here, the same, has a positive charge. It has become a cation. Of course, it does not leave to come here. It stays here because it still pulls this. It acts force in this, but it is less greater than the force that oxygen pulls on this. Okay, I believe we understood it. Now, which substances are called hydrophilic and which are called hydrophobic? Hydrophilic comes from the words hydro, which means water, and philic, which means friendly in Greek. Of course, these are all Greek words, hydro and philic, Greek words, which are substances that dissolve in the water, and these substances which are hydrophilic are the polar one. When we say polar substances, what do we mean? We mean the substances which have polar covalent bonds or ionic bonds. Well, there are substances which are hydrophobic and they will not dissolve in the water, and they are called non-polar substances. And the hydrophobic substances are the non-polar. The hydrophobic are called hydro, which means water, and phobic, which means fear. Phobic, general means fear. Remember the word phobia. Okay. Moving on. Now we will look at the properties of water. First, let me talk to you about the structure of water. Water is a molecule created by the connection of nonpolar covalent bonds between two hydrogen atoms and one oxygen atom. These two are connected. Here are then the polar covalent bonds. We have the delta plus and delta minus we talked before. And this is in an angle of approximately 104.5 degrees. Okay. Now, what happens if we have a bottle of water? The molecules of water will be kept together. Why? Because there are these little dots. What are they? It's another type of bond that is created, which is created between hydrogen atoms and oxygen atoms of adjacent molecules because of the delta plus and the delta minus. This has a slightly positive, this has slightly negative. Therefore, together, there is an attraction, a light attraction though, between them, which is called hydrogen bond. It is hydrogen bonding happens between the positive hydrogen of one molecule, which is attracted to the negative oxygen of an adjacent molecule. And this explains most of the properties we are going to view one by one right now. First, water has a high specific heat capacity. What is specific heat capacity? Is the amount of heat a substance must absorb to increase 1 gram of the substance by 1 degrees Celsius. Blah blah blah. It is actually, it shows us the specific heat, how easy or how difficult a substance can get hot, can absorb heat, can raise its temperature. Water has a high specific heat, which means not really easy. It's difficult for water to change its temperature and needs to receive a lot of heat in order to change its temperature. Okay. Why is that? Why does water have a relatively high heat capacity? Because in order for the temperature of a liquid to be raised, the molecules must gain energy and consequently move about more rapidly. The hydrogen bonds that tend to make water molecules stick to each other make it more difficult for the molecules to move about freely. The bonds must be broken to allow free movement. So, we need more energy to raise the temperature of water than would be the case if there were no hydrogen bonds. Okay? So, is this good? Does this has a biological significance? Of course. Because this means that large bodies of water, such as lakes and oceans, are slow to change temperature as environmental temperature changes. It is more resistant to changes in temperature. That means that the temperature within cells and within the bodies of organisms, which have a high proportion of water, tends to be more constant than that of the air around them. Okay. Let's move on. It has a high heat of vaporization. What on earth is that? That shows us how much energy we need in order to vaporize a liquid. Okay, which means to evaporate it, to make it go from the liquid phase to the gas phase. It needs a lot. Why does it need a lot of heat? Because it has those hydrogen bonds and they need to be broken in order for the atoms to move freely and go away from the liquid in order to become gas. And where do they get this extra heat? From their floor, let's say, from where they're up to, from their environment. Okay? The energy transferred to water molecules during vaporization, results in a corresponding loss of energy from their surroundings, which therefore cool down. This has been used by many organisms as a cooling mechanism, as in sweating or panting in mammals. Now is a universal solvent. We said before here that hydrophilic substances dissolve in water, and we said that hydrophilic substances are all polar substances. Why do they dissolve in water? Why? Let's come and take a look here on this video, this GIF I found. This is sodium chloride. You see, the water has a delta plus and delta minus sign, right? Has a polarity itself. And the water molecules are attracted to the ions and polar molecules of the substance, and therefore collect around and separate them. Okay, this is what happens when a chemical dissolves in water. Once a chemical is in solution, it is free to move around and react with other chemicals, which is how many processes in living organisms take place. Let's see this video. We've got the water molecules with the delta plus and delta minus signs. They go and attract the positive sodium sides. The oxygen, which is negative, attracts the sodium, you see, and it takes it away from the crystal. This is a crystal here. And the same happens with chlorine. The hydrogen, which are positive, attract the negative chlorine. Let's see here. You see, it attracts the negative chloride. Take a look again in the video. Okay, let's go on now. Water exhibits strong cohesion tension. What is that? That means that molecules of water tend to attract one another. Okay? They tend to stick to each other. Why they tend to stick to each other? Because of hydrogen bonds. This explains why water can move in long, unbroken columns through the vascular tissues in plants, and is an important property in cells. Now, high cohesion results in high surface tension. What does that mean? That tiny legs can walk in the water because the molecules of water, because those legs ask a pressure that is less. Let me take it again. These tiny legs can walk in the water because the force they ask in the water is less than the force between the hydrogen bonds. Therefore, the hydrogen bonds don't break and the waters don't get in the water, they step on it. For instance, pond skaters exploit the surface of water as a habitat, and they allow them to settle on or skate over its surface. The pond skater can never break through the surface. Okay? Now density. You see, if we start cooling water and we measure its density all the time, we will see that below 4 degrees of Celsius, the density starts to lower. The density of water starts to decrease. Therefore, ice, which is way below 4 degrees, has a much lower density than water, and therefore it floats in water. Is this important in biology? Of course it is. Because it reduces the tendency for large bodies of water to freeze completely and increases the chances of life surviving in cold collection. Okay, because these things act as insulation. Now let's move on away from the properties of water. What I want you to remember from water is that it is a very polar molecule. This is all I want to stay to your mind. And you can explain now all these properties, having in mind that it's a polar molecule. Now let's see pH. pH is a measure of acidity and alkalinity of a solution. Anything with a pH less than 7 is acidic, and anything with a pH value greater than 7 is alkaline or basic. A pH of 7 is neutral. The value of pH is the negative log of the hydrogen ion concentration in moles per liter. This means concentration. Now, do we have these things in the water? Cations, hydrogen cations in water? We do not. These things exist. What are these things? Let's say we have a water molecule dissolves, okay, and we have these atoms, okay, hydrogen cations. These hydrogen cations, which move freely, will come, which have less charge, will come and stick to this negative O, and therefore this O will have 1, 2, 3 electrons, and this structure is called an oxon. Oxygen with 3 hydrogen ions, and has an overall positive charge because of the H+. Okay. Now, generally, the MEH must be kept stable. This is really, really important. Even a slight change in the pH can be harmful. This is why we need substances that does not allow the change in pH. These are called buffers, and a buffer works by either absorbing excess hydrogen ions or donating hydrogen ions when there are too few. Okay, and they regulate and they help their biological systems regulate their pH. One of the most important buffer is this, because when it needs, it can give this H or it can take one more H. Okay, one more hydrogen atom.